Okay, so let's go ahead and get started. Good morning, happy Tuesday. Hope everybody is surviving the weather this morning okay, especially if you're in Winnipeg. Make sure you stay safe. Okay, so quick review from last time. Arguments are a list of propositions, and if we assume all of our propositions, we want to be able to conclude our conclusion. And we've got two ways of proving arguments. One way would be to use a truth table, and the other way would be to try laws of logic. So let's try each of those approaches and see what we can come up with. So let's start with this first one on the left, see what we can do. Is there a law of logic that we could use in this case? One that sticks out right away, just something equivalent to one of our propositions. De Morgan's law, good. Yeah, exactly what I'm looking for. So this top proposition, we have a not, a negation, outside of a disjunction, and we can push this negation through the parentheses by using De Morgan's law. So I can say that not R or S is logically equivalent to not R and not S. And this is by De Morgan's law. Okay. So now this is equivalent to having the argument not R and not S. S, therefore not R. So now the question is, can we use a different law of logic, or maybe a law of inference to get where we're going here? This one's definitely a little bit trickier because it doesn't pop up directly in one of our laws of logic, but if we start thinking about what this means, we have both not S and S going on here, right? We have this not R, which is good to know about, but we also have this not S. Since we have and, we have both of them. And so if we look at what our argument looks like, remember our argument is a conjunction of all of our premises. So right now, we've changed this to be not R and not S. And my second premise is S. So I like this idea of let's look at an associative law on our argument so we can combine our S and not S. So we have not R and not S and S. These are logically equivalent by the associative law. And what's good about not S and S? Yeah, we've got this law that says not S and S is equivalent to falsehood. So I have not R and false. And now I have a contradiction. So I have not R and false, which means I should be able to conclude R, but So if I was looking to use one of my laws of inference, then I would have hoped that this would have said R, because from not R and falsehood, well, you would want not R implies falsehood there to use that one. But I have a contradiction, which means I have falsehood up here. And what do we know? So we know that this is also equivalent to just falsehood, right? Anything and false is equivalent to false. And what do I know about false implies any statement? Think about the truth tables. Yeah, we've got absorption going on. And now, so this argument, right, all truth values are 0. Now think carefully about our, if we go back to our P, Q, and P implies Q truth table. And if I have 1, 1, 1, 0, 0, 1, 0, 0, P implies Q. If they're both true, that's good. If P is true and Q is false, then P held up its side of the bargain and Q broke the contract. So this is the only place where the contract doesn't work. But when P is false, when P does not hold up its side of the contract, then we say the contract is fine. Remember, this is if you do well in the class, I'll buy you a car. If you don't do well in the class, then whatever happens is fine. So since we have falsehood, since we have a contradiction in our premises, we've already assumed falsehood, which means any conclusion we come to is valid. So yes, this one is valid. It's valid because we got a contradiction in our premises. That's typically not good. You typically wanted to avoid having a contradiction in your premises. And that's because, I'm now looking at my notes carefully, this was supposed to be an and. So let's do this problem again. Start again. Nothing wrong with this problem. It's still technically valid, but I just copied it out of my notes incorrectly. Let's try this again with an and there and see what happens, and hopefully that'll make this make a little bit more sense. And then we will come back to this one next. So let's try not R and S, and also S include not R. Let's try this one again. So same thing, we're still going to start with De Morgan's law, not R and S, logically equivalent to not R or not S. By De Morgan's law. But now we have something interesting going on. We have not R or not S and S. So if we distribute this one, which we can do just as one option, we'll get not R and S, or not S and S. Distributive not S and S is equivalent to falsehood. So this is not R and S, or I'll just write it again, not S and S. This is logically equivalent to not R and S, or falsehood. This is contradiction. Or let's see, what was our actual, flip back in our notes, we'll find the rule for, there's some name for this one. This is one of the names that I don't use all the time and don't have committed to memory. Which one did we call this? Yes, this was an inverse law. I'll label it correctly so it matches your notes. S, not S, and S is the same as S and not S. So this is logically equivalent to contradiction. And now we can use an identity law to say there's no reason to say or falsehood. That doesn't make any sense. Might as well not include it. It's logically equivalent to not R or S. Okay. So now we have not R or S and S. Did I do all this right? Did I messed up in my notes too? Yeah, it looks like I did. Okay, so now we have not R or S, and we can't quite conclude not R from that. How did the and turn into or up here? In step 1, you mean? Or did I flip it here? Yeah. In my distributive law, I got things mixed up. All right, I knew this wasn't working out right. Man, not a great morning so far. Gotta wake up myself. Good thing this is a warm-up. Okay, so this is good so far, but when I do this distributed law, this is still okay. I have and S in both cases. Okay, so this is good. Third to fourth line. Yes. Okay, thank you. That's right. I was hoping that I was going to get an and here. This was an and that became an or by a copy error. This is much better. Not R and S. Now I have not R and S, and I want to conclude not R. But I already have not R. You cannot see anything on the screen. So first, okay, let's pause for a second. Can everyone else see things on the screen? Okay. Good. So, one thing, Ashokwe, you could try is leaving and rejoining. Yeah, I don't know what else could cause it. I'm trying to share. I've synced my view for everyone, so I should be big. Should have a nice big video. Yeah, I'm not sure if you aren't able to fix it for this class. This is being recorded, so you can at least watch it back afterwards, and we can try and work on it together afterwards, but it's the best I got for now. Okay, let's keep going then. So, we've concluded not R and S, from which we can conclude not R. So that is fine. So we do get our conclusion, we are valid. All right. Whew. Let's try looking at this other question. This one, at least, I'm more confident on. We had, just as a reminder, we were looking at R implies S, and S include R. So we tried doing laws of logic. Let's get Is this what we would show on a test for full marks? Yep, this is good. How do we get from, this is a good question, how do we get from not R and S implies R? So let's just add that. Not R and S implies R, not R. I don't know if we have, I have to double check our laws of conjunctive simplification. Thank you. That's the name of it. So one of our laws of inference, if we check our list, it was not one I believe that we mentioned in class just because we didn't go all of them, but in the list of logical implication rules of inference in the definitions and theorems, we have the rule of conjunctive simplification, which says P and Q, you can conclude P. So we have not R and S, we can conclude not R, and that's okay. This is rule of conjunctive simplification. Okay, good. It's back to normal. Everybody can see everything. Good question. Yeah, so this is what we're looking for with these proofs. We want to see the logical equivalences, and if you're using a law of logic, and if you're using a law of inference, we want you to say which one you're using. Okay. So let's switch over to this one. Let's talk about the other way we have of showing whether an argument is valid or invalid. So we can use laws of logic and laws of inference. The advantage of that is we don't have to make a big table. Now, in this case, there were only 3 variables, so our table would only have 8 entries. That's not so bad, but it can get bad, right? It can have a lot of entries in it. And using laws of logic and laws of inference, we can get around that. The downside is there's no pre-prescribed path for a proof that way. A proof using our laws of logic and laws of inference. In fact, there are different ways, different laws, different paths we could have used and gotten the same conclusion to show that that argument was valid. So it's a lot of trial and error. You have to be willing to start something. It doesn't work out. You try something else, try different ideas. Yeah, there. Like I said, there are many different ways of phrasing the end of that last proof. But I want to move on to this one and look at this one in a truth table. So we have R and S. And then as an intermediary, let's look at R implies S. And also R implies S and S. And our argument, if we put our whole argument together, is R implies S and S implies R. This is what our argument claims. So let's look at our 4 cases, 1, 1, 1, 0, 0, 1, 0, 0. And if this argument is valid, answer this question for yourself. What do we expect to happen? How would this truth table show this argument is valid, and how would it show that it's not valid? What are we looking for before we get started? Right, so this argument is valid if it's a tautology, and a tautology means this last column, because this is our logical argument, has to be all true. We should have all ones in this column. If this argument is valid, we get all ones in this column. Okay, so let's take a look. Our first helper column is R implies S. 1 implies 1 is true. 1 implies 0 is false. 0 implies 1 is true. 0 implies 0 is true. Okay. Now we look at R implies S and S. So we're doing an AND of these two columns. 1 and 1 is true. 0 and 0 is false. 1 and 1 is true. 0 and 1 is false. And now we can finally go to our last column, the column we care about. So we want to look at this column implies this column. So is it true that 1 implies 1? Yes, that's fine. Is it true that 0 implies 1? Well, yeah, 0 can imply anything, that's fine. So same down here, 0 implies 0, that's fine. But we do run into an issue here. Here we have 1 implies 0, and that's false. True cannot imply false. So by looking at the truth table, this is not a tautology. There is a case where this is false, where it doesn't happen. If R is false and S is true, we get false out of this truth value. So this is not a tautology. It's not valid. It's not a valid argument. So what happened here? Excuse me. Just as a reminder, one of our laws of inference, good, this is a good question I want to get to in a second. One of our laws of inference was R implies S, R conclude S. This was modus ponens. This is not modus ponens. This is different. I want to talk about the difference between these two things, but first I want to answer this question from chat. Is the only way to show an argument is not valid is to use a truth table. The only way to show an argument is not valid is to find an assignment of the variables that makes it false. You can do that with a truth table, right? If an argument is not valid and you do the whole truth table, you'll always find an answer. But you don't have to show the whole truth table. The part of the truth table that shows this is not valid is just this one line. So all we really needed was this one line. If even one line in a truth table is false, that means your argument is not valid. So really good question. As long as we said the assignment R is false, S is true, makes the statement false, and we showed our work, that would be enough. Okay, so what is the difference between modus ponens, which is valid? This is one of our laws of inference. If we checked it by truth table, we would have a tautology, we would have all ones. And this case, which was not valid. Well, this says, if R then S, and R, we can conclude S. So let's come up with like an English statement for that. If you get an A in the course, I'll buy you a car. You did well in the course, so I will buy you a car. That's how modus ponens works. This argument is saying, if you do well in the course, I'll buy you a car. I bought you a car, so you did well in the course. And that doesn't follow. Just because we have the conclusion does not mean we have the premise. That's what's wrong with this argument. If I promise you, if we make a contract, if you do R, I'll do S, and I end up doing S anyway, that's no guarantee that you ended up doing R at the end of the day. So is there any way to show a statement is not valid using laws of logic and laws of inference? No. Laws of logic and laws of inference only can show things are valid. And this is the problem with, this is what makes them hard. Using laws of logic and laws of inference, you can only prove things that are valid. There's no way to show something is not valid using laws of logic and laws of inference, because using laws of logic and laws of inference, you can just say, okay, well, I tried this and it didn't work. Maybe a different proof, maybe a different argument would work. Maybe I could use different laws. Maybe I could use different inferences to get to a different state. All I know is the one path I tried did not work. The only way we can show an argument is not valid is with an assignment of truth values that makes it not valid. So logic is tricky, right? These are different. One of them's valid, one of them's not. That's why we have to be really careful thinking about these things. So what was going on under the surface in this example is a really common mistake. And it has to do with confusing a statement with a different statement. If I have the statement P implies Q, there are some related statements that we should talk about. The statement Q implies P is the inverse statement. If it rains, I will bring an umbrella. The inverse of that statement is, if I brought an umbrella, it rained. And a statement and its inverse are not equivalent to each other. If it rains, I'll bring an umbrella. Yes, I'm sorry. Definitely want converse statement. I'm looking ahead. Yep, converse statement. Inverse, that's the next thing I want to talk about. Thank you for that catch. Converse statement. Converse is not equivalent to the original statement. If it rains, I will bring an umbrella. Just because I have an umbrella does not mean that it rained. Implications, the reason the arrow only points one direction, which is different than a biconditional, is that the implication only goes in one direction. Biconditional is separate. The inverse statement, also related, is not P implies not Q. This one really is the inverse statement. If it doesn't rain, then I won't bring my umbrella. This is also not equivalent. So let me write down this example I've been saying. P is, it rains. Q is, I bring my umbrella. If it rains, I will bring my umbrella. And the key idea is that I'm allowed to bring my umbrella even if it doesn't rain. Maybe I think it might rain and it doesn't end up happening. If it rains, I'll definitely bring my umbrella, but if it doesn't rain, I'm not making any promises. Which means just because I brought my umbrella doesn't guarantee that it rains. And just because it doesn't rain doesn't mean I won't bring my umbrella. The converse statement and the inverse statement are not equivalent to my original statement. There is one more related statement, however, that is equivalent. This is called the contrapositive statement. And there is one thing I know. If it rains, I'll bring my umbrella. If I didn't bring my umbrella, that means it can't have rained. Because if it did rain, I would have brought my umbrella. So if I didn't bring my umbrella, it couldn't have rained. So the contrapositive statement, not Q implies not P, is equivalent. Let's see why that's true. I'm claiming from P implies Q, we can conclude not Q implies not P. And let's do this one with the truth table again for the practice. So I have P and Q, and my helpers are going to be P implies Q and not Q implies not P. And then my statement is P implies Q implies not Q implies P, not P, rather. And I've got my four cases, 1, 1, 1, 0, 0, 1, 0, 0. P implies Q, 1 implies 1 is true. Not Q is false. False implies anything is true, so that's good. P implies Q, 1 implies 0 is false. Not Q is 1, implies not P, not 1 is 0, so this is 1 implies 0, this one is also false. And then P implies Q, false implies anything is good. Not Q, so this is 0, implies anything is good. And now not 0 is 1, and not 0 is 1, so this is 1 implies 1 is also good. And so now finally I have 1 implies 1, that's good. 0 implies 0, that's good. 1 implies 1 is good. 1 implies 1 is good. I have all 1s here. I have a tautology. This is good. So the contrapositive is equivalent to the original statement. That is inverse, converse, inverse, and contrapositive. Okay. Pause there. Questions about any of these things? Sorry for flipping inverse and converse this morning. Is there a name for this rule? This is the contrapositive. If you said this is true by contrapositive. Does logically implies mean the same thing as is valid? So this symbol means logically implies, and if I put a statement over here and a statement over here, this means P implies Q is a tautology. And we can always write this statement over here as an argument. So yes, if we rephrased this as an argument, if we wrote it in this form, then if P implies Q, this argument is valid. If P logically implies Q, then this argument is valid, yes. Can you use the contrapositive when you're proving arguments? Certainly. If you're trying to show something is valid, the contrapositive is an equivalent statement, so you are allowed to use contrapositive. You're also allowed to use this theorem that we proved, that P implies Q is logically equivalent to not P or Q. This was something we proved in class. This comes up a lot in the homework. Also allowed to use that. Right, so you can use the contrapositive because it's logically equivalent. You cannot use the inverse or the converse because they're not logically equivalent. If you tried to use that in an argument, your argument would not be valid because you're not changing between things that are logically equivalent. Really good question. These are all good questions. Okay, so I want to shift gears a bit. I want to make sure we move on so we don't fall behind. Had to grab more paper. So remember, we were talking about propositions. And we had examples, and we said these two were propositions. 2 is an integer, and pi is an integer. Is there a name? So I've certainly seen implication as disjunction, but in the theorems, and yeah, we call it implication as disjunction. We also call it theorem 1.12 in definitions and theorems. So if you wanted to refer to it by either term would be okay. So we called both of these propositions. One of them is true, and one of them is false. But they're both propositions, and we distinguish that from something like x is an integer, because this statement wasn't true or false, right? It depended on the value of x in order to figure out if it was true or false. However, if we pick a value for x, then this becomes a proposition. If I say, is x an integer? By the way, x was 2, then you know if this is true or not. All right, once you fix x to be a certain thing, sure, it's a proposition. And so we call this an open statement. And this is why we want to differentiate between statements and propositions. So an open statement is a declarative declarative sentence with one or more variables that is not a proposition but becomes a proposition if you replace those variables with a quantity. The variables are replaced with specific quantities from a specified universe. Quantities from a universe. Okay. So x is an integer, not a proposition. It is an open statement. If you fill in the x, it becomes a proposition. And this lets us talk about quantifiers. So two quantifiers we need to know about. One is this symbol, which means for all. And one is this symbol, which means there exists. Okay, so for all x, p of x means p of x is true for every x in the universe. And exists x, p of x, means p of x is true for at least one x in the universe. Okay. So let's look at some examples. Can I please go back a page? Yep. Sorry. Hard to keep too much on the page all at once. But there's our definition of open statement. Yes, so in this case, if p of x is some open statement. So let's look at an example. I'm going to say p of x is the statement x is an integer. This is the open statement we were talking about previously. X is an integer. I also need to specify my universe. So let's say we are in the universe. Universe is all real numbers. So is it true that there exists a value of x in the real numbers such that x is an integer? Is this true or false? True. Good. This is a true statement. There are real numbers that are true. There is at least one real number that is an integer. What about this statement? Is it true that every real number is an integer? Can I repeat the line with the symbols, please? I'm not sure which line you mean. For all, this symbol means for all. This symbol means there exists. This is exists x in the real numbers such that p of x, which is true. And this statement is for all x in the real numbers, p of x. Or equivalently, for all x in the real numbers, x is an integer, and this is false. But of course, the universe matters a lot. Right? Same statement. P of x is still going to be x is an integer, But now I'm going to change up my universe. If I make my universe z positive, so these are the integers that are greater than or equal to 0. So this is 0, 1, 2, and so on. Is it true that there exists an x in z positive that is an integer? Yep, there definitely is. And in fact, is it true that every positive integer is an integer? Still true. So this is what's important about open statements. This is why open statements are not propositions. An open statement isn't true or false. If we quantify it in a universe, it becomes true or false, but it depends on both on the quantifier and on the universe. Just as one more example, if I made my universe the irrational numbers, these are the numbers that are real numbers, but we can't write them as fractions. So Q is the irrational numbers. Those are numbers you can write as fractions. The real numbers are all of the decimals that we can write down. The irrational numbers are numbers we can't write as fractions, things like pi. Then, are there any irrational numbers that are integers? No. None of the irrational numbers are integers. So, unsurprisingly, it is not true that all of them are integers. So, open statements, not propositions. If we quantify them and we give them a universe to work in, then they become true or false. Okay? So I want to talk more about these quantified statements, but let's take our break now. I pushed a little bit longer than usual. So let's just say 2 minutes, stretch, go get some breakfast, whatever you want to do in 2 minutes. We'll come back. We'll talk more about these quantifiers. I'm going to go get some water personally. So 9:21 Winnipeg time. We'll be back. Okay, I got 921 again. Let's jump back in. So, how do we prove how do we show that a statement like for all x, p of x is false? You got a statement that said for all x, p of x, and you didn't think it was true. How would you show that it isn't true? Any thoughts? Yeah, good. All we need to show for all x, p of x is false is to find an x in the universe, that's important, for which p of x is false. You only need one x. If you can find a single x that makes p of x false, as long as it's in the universe, then the statement for all x, p of x is false. As an example, you could say every number has the letter E in its English spelling. We can turn this statement into an open statement. We can turn this sentence into an open statement. So P of n is the statement, the spelling of n has an E in it. And we can translate this sentence into for all n. I said number here, maybe that's not specific. Let's specify a universe. Let's say I'm only talking about the non-negative integers. So for all n in z greater than or equal to 0, p of n. Okay. So is this statement true or false, and how do you know? Good. It's false. And to show it's false, we just need to pick an example. And the example that we pick doesn't have to be the same. So there's two great examples in chat. 2 has no E, 6 has no E. Now there's a third. 4 also has no E. We can pick whichever one we want, one of which is 50. Let's go with 50. I like that one. False. 50 has no E. Or in other words, not P of 50. Okay. On the other hand, proving a for all statement is true is a lot harder. If we want to show a for all statement is true, we need to show that it holds for every x in the universe. and there could be infinitely many. Your universe could have infinitely many things in it. So I want you to think about this statement. So that was P of n. Here's my next statement. Q of n. My statement is the same. I'm sorry. I'm changing my universe. Still P of n, but now for every n in the odd numbers, these are the odd numbers, P of n. So now you start thinking about it. 1 has an e in it. 3 has an e in it. 5, 7, 9, 11, 13, 15, 17, 19. And then we get up to 21, 23. Well, okay, all the 20-somethings have e's in them because the 1, 3, 5, 7, 9 had e's in them. And same for 30 and 40 and 50. And then we get up to 100 and, well, it starts with 100, that has an e. I can't find any examples that make it false. But that doesn't mean I've shown it's true. In order to show it's true, I'd have to check every odd number. And there's infinitely many odd numbers. So it's much, much harder to show that this statement is true than it is to show it's false. To show it's false, you just need one counterexample, is what we call it. 50 is a counterexample. 6 is another counterexample. But counterexamples don't help if you're trying to show something is true. If you're trying to show something is true, you need to show it's true for all possible cases. This is harder. We'll come back to it. First, I want to talk about exists statements as well. How can you show that there exists an x such that P of x is true? How do I show there exists a number such that the spelling of n has an e in it? Just pick one. This isn't even a counterexample. It's just an example. Right? I want to show there exists an x in positive z or non-negative z such that P of x, my example is x is equal to 5. 5 has an e in it. Oops, I'm off the bottom of the page. Found it. There it is. There's my example. So proving that an exists statement is true, pretty easy. Just find the example. Now I think you can all tell where I'm going with this. How do we show there exists an x, P of x is false? So for an example, there exists an x in the odd numbers, the positive odd numbers, such that not P of x. there is an odd number that does not have an E in its English. English expansion. It's the same as the last time. You need to show that none of the X satisfy. Or here, I'll keep this consistent, is false. Need to check that every X is false. Makes P of X false. So here's the connection I want to draw. These seem related. If I want to show that a for all statement is false, I just need a counterexample. If I want to show an exists statement is true, I just need an example. But if I want to show a for all statement is true, I need to check everything. And if I need to show that an exists statement is false, I need to check everything. So this tells us how these two concepts are related. The negation of a for all statement, if it's not the case that something is true for every X, that is the same as, logically equivalent to, there is some X where P of X is false. So not P of X is true. The opposite of for all X, P of X, is there exists X, not P of X. And relatedly, the opposite of there exists an X that makes P of X true is logically equivalent to for all X, not P of X. So this is why proving for all statements and disproving there exists statements are both hard, because you're sort of doing the same thing. You're checking every case. And why proving exists statements or disproving for all statements are both easy, because you're just looking for an example in each case. Okay. So how do we prove for all statements? And here's our important tool. The important tool is the Rule of Universal Generalization. The Rule of Universal Generalization says, if you pick something out of your universe, and the only properties you use when proving something about it is that it happened to belong to that universe, then you've actually proved something about every member of that universe. So a statement about an arbitrary member of a universe holds for every member of that universe. Okay. So here's an example. my P of n is going to be the statement n is an even number. And my definition for an even number is that 2 divides that number with no remainder. So now I want to prove the statement for all n in the non-negative integers p of 2n. Okay, I want to show that this is true. That's my goal. And to do it, I'm going to use the rule of universal generalization. So I start off by picking any even number. Picking any number. Pick any n in the positive integers, the non-negative integers. Any n in z greater than or equal to 0. This is theorem 1.20 in 1.5. I'm doing the quantifiers in a slightly different order than we do them in the notes, but we are getting to everything. So pick any non-negative integer. If I take 2n and I divide it by 2, I get n left over with no remainder. So that means P of 2n is true for this specific n that I picked. All I did was pick one n. I'm not checking all n all at the same time. I'm just picking one n. But when I picked that one n, I didn't make any special requirements on it. All I said is it's any n belonging to this family, any n in this universe. And since there was nothing special about this n, and P of n was true for this one particular n, by the rule of universal generalization, for all n, P of 2n is true. This is how we end up proving for all statements. We want to use the rule of universal generalization. I pick any number, any element of my universe. I show it's true for that one that I picked. And since there's nothing special about that one that I picked, that means it must be true for every element of my universe. So if we go back to this statement, every odd number has the letter E in its English spelling. Why is that true? Well, pick any odd number. I need to show just picking any odd number, I can find an E in it. One specific odd number without any additional requirements. That means every odd number has an E in it. Now, that's a little bit harder to prove. I'd have to break it down into lots of different cases, but I can still do it with this rule of universal generalization. But what if it was just P of n, you randomly selected an even number? It would come out as true despite the whole thing being false. So let's go into that example. This is a good question. There is a little bit more I want to say, but let's see if I can get this done. But this is a really good point. can we prove for all n p of n this way? So I pick any n in z greater than or equal to 0, and I look at n divided by 2. Oops, I'm off the bottom of the page again. If n is even, this has no remainder. So if the n I picked happened to be even, have I successfully proved for all n p of n? And the answer is no. I picked n to be any element of my universe, but then I had to add another requirement. It's this additional requirement that makes this proof break. Because I had to add a second requirement here, it's no longer true for any arbitrary n. It's only any arbitrary n that is also even. In this last example, once I picked my n, there was nothing else I had to add. No other properties were required. Just that this n that I got as my division was a whole number, because it started as a whole number. So this is why it's really important to make sure you're not adding any additional requirements. Okay, one last thing I want to say in today's class is how do we use this to show exist statements are false? How can we use the rule of universal generalization to show exists x, p of x is false? And we can do this with a proof by contradiction. Because not there exists x p of x is logically equivalent to for all x not p of x. We can disprove existence statements by instead proving a universal statement. And then we can just pick any x arbitrarily, show not p of x is true, use the rule of universal generalization, and now that's equivalent to showing not there exists x p of x. Okay, good question from chat. How would you know if there's requirements to fulfill the rule of universal generalization? It's exactly this additional requirement we had here. This was only true, n over 2 has no remainder only when n is an even number. If n is an odd number, then this does have a remainder. So if you want to say this has no remainder, that's true, right? 2n, the 2's cancel, there's an n left over, there's no remainder. Here, you can't cancel a 2. If you're claiming this has no remainder, you needed to know n was an even number. That's the additional requirement. Okay, so that's 9:45. I'm out of time there. We'll talk more about quantifiers in Thursday's lecture. I'm hoping we'll also start induction on Thursday's lecture, but a little bit more to say about quantifiers next time. See everybody then.